Hey guys, I'm Won. So last time I checked, I was still an engineer on the observability team here in NYC. I specifically work on the Jaeger team, which is the distributed tracing system that we built here internally in New York. So today I'm going to talk about sampling with Jaeger. I'll do a quick overview of the agenda. So we're going to just do a very brief overview of distributed tracing for any newcomers here. And then we're going to start talking about sampling and the different sampling strategies that Jaeger provides. Then we'll do a quick XYS demo. So XYS is an internal service that we use internally to gain insight into latency distributions and traffic patterns of Uber's microservices. And then we'll finish with some booing and Q&A. All right, so, just a show of hands, how many people are familiar with distributed tracing? Okay, I'll just do it super quickly. So a trace tells a story of a transaction or a workflow as it propagates through a distributed system. So in this example that we have on the left is a call graph, right? So service A resides in your data center, and it's an edge service, right? So from the internet, you get a request to service A, and then service A makes a request to service B. One thing to note that is service A needs to wait until service B responds before it can make progress. Service B then calls service C, and service C then calls service D. And once B gets all the responses, then it responds back to A with whatever, right? Then A makes a call to service C. So from here, you can actually see the call graph itself shows you an embedded ordered relationship between all the separate services. One thing to note that is that each of these services will emit something called a span. Okay, so what is a span? A span represents a logical unit of work in the system that has a name, a start time, and a duration. A trace is composed of multiple spans, each of which represents the work done by the respective service during the lifetime of the transaction. So this slide is just showing that we want to visualize the trace with the graph on the right side, as that allows you to see latency and other aspects of timing. Where the call graph on the left, you can't really discern that information. Okay, so we distributed tracing. So what is it good for? Here we have a dependency graph of a subset of microservices at Uber, and it was generated via distributed tracing data. Let's assume that distributed tracing didn't exist, and then let's see what the life of a normal on-call engineer would look like. All right, so say hi to Bob. So Bob is a new engineer at Uber, and he's been put in charge of this red service in the graph. Right? It's his first night on call, and an alert fires saying that one of his endpoints is timing out. So what does he do? Right? So instinctively, the first thing he does is he goes to the metrics dashboard. Right? And then he checks out that that the endpoint has increased latency. So far, all Bob has accomplished is to confirm that the alert was not a false alarm, right? He hasn't done anything useful yet. The other on-calls for the other services that depend on Bob's service are now spamming his chat, asking him, why he broke everything, why is he such a bad engineer, right? So Bob doesn't panic, and next he goes to the logs, right? So he jumps onto one of the hosts that's running the service and pulls up the logs. He searches for keywords such as failure, error, and 400. And then luckily he finds an error log that says there was a get call that was failing due to a timeout. So what he discovers is that his service, which is the red service to remind you, is hitting the blue service, and the blue service is the one that's timing out. So he responds back in chat and says, oh, it's the blue service's fault. It's not my fault. Just go talk to those guys, right? So unbeknownst to Bob, the same conversation is happening all across Uber as on-call engineers for all the blue services are trying to debug why their endpoints are timing out. One thing to note is that only the on-call engineers for the blue services are seeing this timeout issue. The service owners for the yellow services, don't actually see any issues with their service right now. There's no service degradation. Can anyone guess as to why that's happening? Why only the people? So blue services, service degradation, yellow services, they don't see anything. Everything is fine. So blue is calling out to the yellow service. So the line points to the service that you're going to call. The blue services are all directly or indirectly dependent on the problem service, right? So in this graph, the problem service is actually the green service, right? So the actual issue in this case was Cassandra, the green service. So one of its nodes died, and the other nodes were just having a hard time keeping up. So the latency increased for everyone. So let's now think back to Bob, right? So why was Bob having such a hard time finding the root cause of all his timeouts, right? So all he did was just pass the bug down to the next guy in the chain, right? And then all the other engineers did the same thing. The logs and metrics that he used just presented a very microscopic view of his service and like just its dependencies, like maybe one jump down. So logs and metrics aren't going to tell you the issue is 5 jumps away from you. The only way Bob could have diagnosed this issue through just logs and metrics was had he had memorized his dependency of 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 his dependency. Had he had memorized those and had he had known like the last one in that chain is Cassandra, and that's the one that usually times out in the first place, and that's the first place he looks, there was no other way that he could have diagnosed this with the tools that he had. So now let's assume that Bob actually had access to distributed tracing, and we'll see how trivial this makes discovering root causes of an outage. All right, so this is just a Jaeger trace of the red service, right? So you can see that there's a red service, that's the top service, and it's calling blue 1, blue 2, etc., right? And all the blue services are all the services down the chain. And at the end, we have a Cassandra call. So if you look at the trace, it took about 350 microseconds, and out of that, around 230 microseconds were taken up by Cassandra, right? So about 70% of the trace. Now let's look at a trace that happened during the timeout outage, right? So you can notice straight away that the duration of the trace increased from 350 microseconds to 1,000 microseconds, and also the Cassandra duration increased from 230 microseconds to 820 microseconds. The other thing to note is that now that there is a red exclamation mark next to the Cassandra span, Jaeger allows users to annotate their spans with errors. So the error tag, all it's saying is just like it's a special tag that forces the Jaeger UI to add the exclamation mark so that engineers will know where to look. Oh, well, it'll draw the eye of the engineer, right? So all Bob had to do was to compare these two traces instead of going through metrics and logs. And then he would have immediately seen that there was an issue with Cassandra, right? So this isn't to say metrics and logs are useless. No, it is. Metrics and logs are useless. No, but without distributed tracing, those tools are ineffective at discovering the root cause in a larger distributed architecture. So now that everyone's an expert in distributed tracing, we'll start talking about sampling. So what is sampling? So sampling is just the selection of a subset of individuals from within a population, so that with the aim of using the subset to estimate the characteristics of the entire population. So what does that mean in terms of distributed tracing? That means that we sample just a subset of traces, then use those traces to figure out the traffic patterns of the entire service diagram. So, okay, so why do we even bother sample at all, right? So why can't we just collect all the data? So there are 3 main issues for that. So number 1 is that we want to limit the runtime and storage overhead for the service that's instrumenting the service. Starting a span and emitting it for every single request will add a non-negligible amount of overhead to your service. So if your service is performance critical, this is a no-go. Secondly, we want to limit the Jaeger storage overhead. So Jaeger uses Cassandra to store traces and data and spans, but performant SSDs do not come cheap. And although Cassandra scales well horizontally, it doesn't scale well financially. Lastly, we want to limit the network overhead. Whenever we emit a trace or span, we need to get that to Jaeger for storage. If we were to sample everything, your network will be taken up by Jaeger spans, and the actual RPC payloads that are important to your business will suffer from that. So let's just talk about how sampling works. So the root service makes the sampling decision. Then this decision is passed down to all the other services in the call graph, right? The sampling decision is made based on the sampling strategy. And on the next slide, I'll go into what the sampling strategies are. One thing to note is that the sampling decision is binary. Either all services sample or none of the services sample. Okay. So here are some of the sampling strategies that Jaeger provides. There are others, but we're just going to talk about these 2 for now. So the rate limiting sampler what that does is, let's say you give it a certain rate, let's say 10 traces per second, then Jaeger will generate at most 10 traces a second, right? So this sampler is essentially upper bounding the number of samples that you can generate. Next up is we have the probabilistic sampler. So as the name implies, this one is based on probability. This is the default sampler that Jaeger uses. Every service is assigned a global default probability of 1 in 1,000. So what this means is that for every 1,000 requests you make, you expect there to be at least one sample trace, mathematically speaking. This is the model that we had originally, and there were a couple of downsides to it. So traffic patterns fluctuate widely across the services in the company. What happened was we had a team approach us, and they were writing a new endpoint, right? So the original endpoint was start trip v1, and they wanted to move over and migrate to start trip v2. And they wanted to use Jaeger data to figure out if there were any regressions in the new endpoint. The issue was that since they weren't sure how performant start trip v2 was, they didn't give it that much queries per second. They didn't siphon off a lot of queries per second to that endpoint, right? So given that the sampling probability defaults to 1 in 1,000, the issue we were seeing was that for the start trip v1 endpoint, given its QPS, we were expecting to get 1 sample a second. But for the start trip v2 endpoint, given the low QPS and the low probability, we were expecting a sample once every 1,000 seconds, which clearly didn't work for them. So ideally, both endpoints should be assigned different probabilities so that they both generate the same number of samples, right? So that's the model we move to next. So let's say our goal is to generate 1 sample per second. So depending on the QPS, we will generate a new static probability for each of the endpoints. So for start trip v1, since we want 1 sample a second, we actually don't modify the probability and we just keep it as is. But for start trip v2, since we weren't getting enough samples, we just increased the probability to 1, and the math worked out where the expected number of samples was 1, right? So this, in theory, should generate the exact number of traces that we want. So that solution didn't work as well because QPS for endpoints are never static. So we have this graph here that shows QPS for the start trip v2 endpoint. You can see that every 3 hours is a traffic spike. Given that we assign it a probability of 1, which means we sample everything, when there are traffic spikes, unfortunately, we were forced to sample everything, which as I mentioned before, leads to increased performance overhead and Jaeger degradation. So this is why we built adaptive sampling. Adaptive sampling has 2 main goals. One was to guarantee a minimum number of samples for all endpoints. And the second was to scale the sampling probability with endpoint QPS. So if endpoint has high QPS, then we want to assign it a low probability. And if the endpoint has low QPS, then we want to assign it a high probability. So let's look at this rudimentary graph below. Each Jaeger client will receive a certain amount of throughput, right? And we denote that as QPS in this graph. That QPS is sampled using the sampling probability, which gives us the sample QPS, right? I think that makes sense, okay. So the goal of adaptive sampling, which is this magic box, is to calculate a new probability such that the sample QPS is equal to the target QPS, right? So the adaptive sampler will continuously adjust the probability to account for QPS fluctuations. So now let's dig into how the magic is implemented. All right, so if anyone's familiar with like control theory, the feedback loop diagram in the previous slide should look similar to a PID controller. So a PID controller is a control loop feedback mechanism that continuously calculates the error between the target state and the current state. And then it applies a correction term based on the PID terms. So I won't bore you with the details of how the PID terms all work. There are plenty of good articles out there that explain it. Okay, so, sorry, yeah, go ahead. All right, I is integral, D is derivative, P is proportional, yeah. So essentially what's happening is one of the terms takes into account what's happening right now. The other term takes into account what happened in history. So it takes a longer look back. And the last term is looking forward into the future, right? So now let's map the PID controller to the diagram we just saw. Like the controller calculates the error between the target QPS and the sample QPS. The error is input into PID terms, which will output the probability. which we then forward to the client, and then the cycle repeats forever. Before we go any further, I have to just take a quick detour and go through the Jaeger architecture, as some of the problems that we saw with adaptive sampling after we built it actually stem from some of the design decisions that we made in the architecture. So this large gray box is the host or container on which your service is running. So let's first look at the data flow through the system first. So that's the blue lines, right? So the yellow box is the application that's being instrumented with Jaeger. When a span is emitted, the Jaeger client forwards the span to the Jaeger agent that runs on every host. Then agent then forwards the spans to the collectors, which handle sanitization and then persisting the storage to, persisting the span to storage. All right, now let's look at the control flow, which are the red lines, right? So the Jaeger collector keeps track of all sampling decisions, sampling strategies, in memory. So what happens is once every minute, the Jaeger clients will request the sampling strategy from the Jaeger agent, which in turn will fetch it from the Jaeger collector. So notice how the data flow is push-based, the blue lines. So agents, the clients push the spans to the collectors. And also notice how the control flow is pull-based. So the Jaeger clients pull for the sampling strategies. So, and this exact pull design is the cause of some severe problems that we have in adaptive sampling. Okay. Unfortunately, traffic spikes still affect adaptive sampling. So since the clients pull once a minute for sampling strategies, we can still potentially oversample until the new sampling probability is calculated and forwarded to the clients. So here on the top graph, this graph represents the traffic of an endpoint, and the bottom graph represents the probability that adaptive sampling is calculating. So as you can see, there are regular traffic spikes in the top graph, but then between those traffic spikes, there are little to no traffic. So what happens is that while the traffic is non-existent, adaptive sampling will gradually raise the sampling rate until the number of samples reaches the target QPS. Right? Unfortunately, this means that when there is a traffic spike, we sample everything before the adaptive sampling can react in time and lower the probability. So the current implementation of adaptive sampling can handle gradual modulations in the traffic patterns, but it can't handle traffic spikes. So what have we done to go about solving this issue? So the most simple solution would be to upgrade all the clients across all services to use a shorter polling interval. So let's say they fetch sampling strategies every 5 seconds or 10 seconds, right? So unfortunately, at Uber scale, that isn't as easy as it sounds. So we have over 4,000 microservices, and we don't have a mono repo where you could just update a dependency and next time someone makes a deploy, it automatically updates, right? So also teams have different deployment cycles, and certain services are in maintenance mode, and they won't upgrade it or touch it. So to get all services to upgrade would take a directive from the CTO. So apart from this, what can we do? Right, so we have something in the pipeline called rate limiting adaptive sampling, which we're in the middle of a theory craft. So up till now, we've spoken solely about adaptive sampling using probabilities, right? So now we're talking about using a hard upper bound rate. So how would this even work? So going back to the PID controller, instead of generating a probability, we're now just calculating a rate, right? All the other inputs and outputs, they remain the same. So how is this any different, right? So what this guarantees is that it will prevent oversampling during traffic spikes. And at the same time, it also guarantees a steady stream of samples. So additionally, this solution is more easily deployable for us since it doesn't actually need a release of all the Jaeger clients. Instead, the existing clients can just receive a new sampling strategy from our end. So for us, it just boils down to just one simple not simple, but one backend change, and that will upgrade, and it's easier than upgrading 4,000 microservices. One of the issues we're dealing with right now is trying to understand whether or not this new rate limiting sampling will generate random samples. So what do I mean by random samples? So if you recall, we want to estimate the characteristics of the entire population using from extrapolating from the samples, right? But this is only possible if the samples are chosen randomly. Right? So using a probabilistic sampler, each trace has an equal chance of being sampled. right? So any extrapolation that we do on it will be characteristic of the entire population. So to break this down even further, if we were to sample 100 traces, and one trace has an abnormal latency, we can assume that 1 in every 100 requests will also have this abnormal latency, right? So the rate limiting sampling that we are planning on using is called systematic sampling. So this sampling starts by selecting an element from the list at random, right? And that's the starting point. Then at every other kth element, that element is selected for a sample, as a sample. Right? So according to statisticians, systematic sampling is to be only applied if the given population is homogeneous. And because this allows the samples to be uniformly distributed over the population. Right. So the caveat here is that statisticians have widely condemned systematic sampling in favor of random sampling. So why do they do this? So let's say let's say we're picking some random samples from the sign graph that we have here, right? So if we chose a bad starting point and a bad K, what we end up happening is we only pick the red samples, right? Which isn't characteristic of the entire population. And then our inferences will be completely off the mark. So at Uber, well, I personally am currently trying to discover if production traffic is homogeneous so that an approach like rate limiting adaptive sampling can work. Now let's look at XYS, which is a internal service that we use that uses Jaeger traces to extrapolate latency diagrams and other traffic patterns for your services. So in this, this is a screenshot of an XYS latency histogram. So what are we actually seeing here? So the y-axis shows the duration of a request on a log scale, and the vertical axis shows the actual number of requests. So it's not showing the actual number of traces, it's showing the actual number of requests, right? So from a trace, how do you extrapolate the number of requests that a single trace represents, right? So let's say a trace is sampled with a probability of 1 in 10. This means that for every 10 requests, there should be one sample trace, right? One sample trace, right? So therefore, if we see a sample with a probability of 1 in 10, a sample that was traced with a probability of 1 in 10, then we can say that that trace represents 10 requests. So this is a bit hand wavy, but I've been told by mathematicians that this is sound. All right. So what we're seeing in this graph is the latency histogram of one particular service. So to break that down a bit, this is showing the number of requests bucketed by duration. So for each trace that we sample, we estimate the number of requests it actually represents. Then we bucket it by that duration, and we plot it in this graph. So I can do a quick demo now. All right, so for this example, we're gonna use a dummy app called Hot Rod. It's an ad that allows you to order a car at a click of a button. I personally don't think that business model will take off, but there it is. Okay, so what you can do is you can order a car by pressing these buttons, right? So, oh, sorry, let me get rid of that. Let me get rid of that. All right, so as a service owner, we're actually interested in like the underlying wiring of this application. So what we can, luckily for us, this service is instrumented with Jaeger. So we can actually go and to Jaeger, and we can see the traces that it generated, right? Cool, these are the traces. So we can just open one of the traces up, and we can see that the front end service is hitting the customer service, which is calling MySQL, and there are also Redis calls over here, and then there are other front end routing calls as well, right? So looking at individual traces doesn't help with inferring the characteristics of the entire service, right? So what we can do is now we can go to XYS. And XYS provides, so XYS stands for examine your service, I'm sorry. So what you can do here is you can see dependency graphs, and this is per service, but you can also see dependency graphs based on service and endpoint. So it breaks down into customer and, well, you can actually see the exact endpoint that we're hitting. Okay, so let's look at the latency histogram now. Okay, so what we can do is we can break it down by this endpoint. Okay, so if you're an engineer on this service and you see a latency histogram that looks like this, like there's something weird going on, right? So half the requests take around 600 milliseconds, and the other half take over around 2 seconds. Sorry. So what can we do to debug this, right? So one thing you can do is we can actually drag over here, and we can actually see the traces that are characteristic of this behavior. So we can actually open these traces, and I'll go back to Jaeger, then we can open one of the traces, right? Back in XYS, we can also get samples from traces that took a lot longer time, right? So then we can find these traces, and let me just move it over here, right? Then we can now go in and compare these two traces and figure out what was going on. So the biggest issue that I see here is that this MySQL call, right? So this MySQL call is taking 1.54 seconds, while in the first call, where the latency was low, it's taking around 300 milliseconds, right? So let's see if they've traced, they added any useful tidbits for us so that we can figure out what's wrong. Okay, so if we expand the logs and of the span, we can actually see it's waiting behind 4 transactions. And then once it's acquired the lock, after the other transactions are finished, then it can go ahead and do its work, right? So what this XYS allows you to do is it allows you to infer behaviors. So we are in the midst of building something that does what I just did, rather than me going in and personally comparing 2 traces basically automatically, and it just shows you the diff. And then from the diff, you can just figure out, oh, this is where there's something anomalous going on. Oh, no, okay, never mind. All right, cool, thank you.